Looking a little closer at the retina. Now we know the retina was the internal of the three layers we already mentioned. But the retina itself is actually a two-layer system. So you have two different layers that make up the retina. Now both these layers are very thin, but the first layer is the pigmented layer. Now the pigmented layer is the outer layer that's absorbing light. Well, you're saying, why do I absorb light? You're trying to prevent light from scattering. Because if light came in and started bouncing around, you get the same image every place that light hit. So really you're trying to make sure you don't have light scattering. And that works in conjunction with the iris and the pupil. Because the iris tries to close down to balance the amount of light coming in so this pigmented layer can absorb it all. Maybe you've seen an example where it hasn't worked. If you've ever seen a picture where someone has red eye, you know, that red dot in each eye, that was because the light was overpowering. So let's say the flash goes off on the camera, light comes in. Well, if the flash was going off, that means there wasn't a lot of light to start with. So the eye, the pupil, was larger. But now you add this massive amount of light from the flash, the eye doesn't have time to constrict. It's too fast. So the light goes in, the pigmented layer can't absorb it all. So some of that light starts bouncing around and bounces back out. As it's bouncing out, the redness is because you're seeing the back of the eye. You're seeing the red of the blood vessels in the eye. So for that split second there, the light is bouncing back out of the eye and it's looking like it's red because of the red pigmentation. That's why some cameras will have that little pre-flash, that little stutter flash, and then a real flash. But if you want to get away from it, simply make sure that the light source isn't directly in the eye. If it's off the sides coming in, it can't bounce back out again. So this pigmented layer, 99% of the time, it absorbs all the light because the iris controls how much light is coming in. The second layer is the neural layer. So again, both part of the retina. The neural layer is where you have your photoreceptors. These will be the rods and the cones. They're going to transduce the light energy and convert it into signals your body and your other cells can understand. But in this neural layer, you'll also have these bipolar cells, these ganglion cells. They're all helping to relay what that sensory input was. So the rods and cones transduce the light energy. They then send those signals into the bipolar cells and the ganglion cells. So it kind of looks like this. These two structures right here, those are the cones. Well, all of these thinner structures are the rods. You can see how they're all synapsing with these bipolar cells, which then are synapsing with the ganglion cells. So that means that this top area is the pigmented layer. This area is the neural layer. But notice the very bottom, the direction of light. Light is going in this direction. That means light is passing through the neural layer, heading towards the pigmented layer. That pigmented layer then absorbs the light because that's where the ends and the receptors are for your rods and cones. They're right nestled into the pigmented layer. So light's passing through the neural down to the pigmented layer where you have the rods and cones waiting to transduce the light energy. So those ganglion cells, they're the ones that were at the very outside edge. They're on the inner surface of the retina. Their purpose, take that signal and run it all the way through to the optic nerve. That's great, except that's what creates the blind spot. Because you're looking at these hundreds and thousands of all these ganglion cells all going to one spot. So that optic disc is where they all meet. That's where you get your blind spot. It's because every single neuron has to leave the eye someplace. You can't have them simply leaving every which way because it have problems with the structural integrity. So you have them all leaving in one cluster, which is the optic nerve. So you can see this is your optic nerve. That means this is the blind spot right in front of it. Because you can see the sheer number, all these lines are all neurons. So all those neurons are leaving at that one single spot, creating the blind spot. All right, the rods. Now the rods are best in dim light. They're very sensitive to light. So this is more your night vision, when it's dusk outside. You're not really using the rods when it's bright and sunny, or if you're in a brightly lit room, because they absorb all wavelengths of light. But intriguingly enough, the input is gray tones only. Think about if you've ever been out at dusk or just barely enough light to see. Maybe you're moving around the house at night. Do you see the colors of everything around you? Not typically, unless the light levels come up a little bit. And once you start increasing the light levels, it's not just rods anymore, because if you're seeing color, that's going to the cones. So the rods are only in dim or more of a night vision scenario. And these rods, they kind of sum up the visual input, which results in this fuzzy and indistinct images. That's why if you're in very dim light at night, you can kind of see shapes, but do they look crystal clear? No. Because multiple of these rods are all feeding into one single neural interface. That means all the information coming in at these 3, 4, 5 points gets relayed to one cell, so therefore acts as one single input. So if you had these, let's say 4 different rods here, and there was an edge of a structure right here, well, these 2 and these 2 would pick up the structure, 2 wouldn't, but together they all create the same image. So it ends up creating kind of like a fuzzy outside edge image sometimes. So those are your rods. The cones need more light. They need bright light. They can start working when it's a little dimmer, but the brighter it gets, the more vibrant the colors get, the sharper the image gets, because they have a hugely vast array of vivid color inputs. Now, each one of these cones will have an individual synapse. That means each cone will have a single signal heading in. So if you have a cone, and a cone, let's say you have 3 cones out here, each one has its own ganglion cell, which means each one will have its own input going to the brain. That allows for sharper vision. You can see exactly when something ends because this cone and this cone aren't tied together. They're unique and individual signal inputs. So the cones are more like a high definition vision. It's when you can really see the crystal clear imagery. The dimmer the light, the fuzzier the image gets, until all of a sudden at night, when it's pitch black out, you can barely see the images in grayscale and not the clearest. But cones, bright light, plenty of light, see color, that's what the cones are. So a little about the retina and its neural inputs.